Okay, now that we have spoken about circuits, about parallel connections and series connections, I want us to talk about batteries, more specifically internal resistance. To begin, let's understand what batteries are. Now, batteries are energy storage devices that use chemical reaction to produce electrical energy. Now, they consist of one or more cells. In this, I will draw two cells. That's one cell, and that will be my second cell. Now, they consist of one or more cells, each containing an anode and a cathode, an electrolyte. Now, a battery can have one cell or it can have more cells, and each one will have an anode and a cathode. It will have a positive and a negative terminal. Now, I use either the short or the long line here to show which one is the positive and which one is the negative. Now, when a battery is connected in a circuit, it will generate electrical current as electrons flow from the anode to the cathode. Remember, the battery will have what we call internal resistance. Now, imagine even in a perfect conductor, there's a tiny bit of resistance. Similarly, within batteries, there's internal resistance. In most circuit drawings, you'll just see the two cells and then the conductor will be connected there. But in this case, I will introduce internal resistance. So I will use the same symbol as resistance, but a little smaller one, and connect it to the cell. Now, not only the cells now make the battery, the cells and the internal resistance now make my battery. And I will show my battery by using these dotted lines. Now, instead of just cells, this entire thing will now be my battery. Now, it will consist of cells, one or more, and each having an anode and a cathode and electrolytes, and it will have internal resistance. Now, this internal resistance is kind of a traffic jam for electrons due to factors like electrolyte resistance and electrode interfaces, but you won't discuss that in this module. So, a battery consists of cells and internal resistance. And as these electrons flow externally, this resistance will become the traffic jam. But inside the cell itself, this internal resistance will reduce the flow of the electrons. Now, because this internal resistance limits how quickly electrons move, it will create a voltage drop within the battery itself when current flows. So if the entire battery was supposed to give us 10 volts, because of this internal resistance, there will be a voltage drop and it will give us maybe 8 or 7, depending on the calculations that we will discuss as we move through the module. Now, the internal resistance isn't just a concept, it has real effects on the battery. Firstly, it causes a voltage drop as current flows. So remember with Ohm's law, to calculate the voltage, you will take voltage is equal to current multiplied by resistance. Let's say you have voltage load. Now this V load will be the external voltage. Load means that external resistance in a circuit. Let's write that down. External resistance in a circuit. Now, because of my external resistance, let's say your V load is given by current multiplied by resistance. Because of internal resistance, the voltage under load might be lower than its no load voltage. Now, the no load voltage will be the internal voltage inside the battery itself, and that will be given by the current, the total current of the circuit multiplied by the internal resistance. Now, we still use Ohm's law, but instead of using the external resistance, meaning that it gives us the V load, we will use the internal resistance. And this internal resistance, we will denote it using a small r instead of a capital R. A capital R is external and the small r means internal resistance. Now, secondly, internal resistance leads to energy losses as some electrical energy is converted into heat due to electron collisions. Now, the more you use a battery, you will feel that it gets warmer and warmer, even when your battery is inside of a cell phone. The more you use your cell phone, the more your cell phone will get warmer. This is because of the electron collisions inside your bed. Now, that causes energy losses in the form of heat. Remember, energy cannot be created or destroyed. It can only be converted. And in this case, that energy, electrical energy that is in a battery will be converted into heat, and therefore you will feel your devices getting warm. So how do we relate the V load and the internal voltage? So the way that we are going to calculate it, we are going to introduce EMF, the electromotive force. Now, EMF, I'm going to denote it using this symbol. Now, I may have called it an electromotive force, which is what EMF means, but it is not just a force. It is not actually a force. Rather, it is the potential difference between the terminals of a battery when it's not connected to a circuit. Now, if you have your battery, an actual battery like this, and you calculate the potential difference between the two terminals, you get what we call the EMF. Think of EMF as the push a battery provides to electrons. Now, we said that for the battery to provide electrical energy through the circuit, the electrons will have to flow. Now, they won't just flow out of nowhere. Inside this battery, you have the EMF, which will sort of push these electrons so that they have to move. And once you have electrical energy, then that process will power itself up, and then it will become a loop. So this EMF, it will push the electrons, encouraging them to move from negative terminal to a positive terminal. Now, the negative terminal, we call it the anode, and the positive terminal, we call it the cathode. So it's like the starting point of the battery's life. Now, EMF and internal resistance, this small r, they dance together inside the battery. When you connect a battery to a circuit, the EMF tries to push electrons, creating a potential difference. However, the internal resistance acts as a speed bump, causing the voltage drop and impacting the battery's effective voltage. So this means that the voltage across the terminals under load, because of external resistance, might be lower than the no load EMF due to internal resistance. Now let's link them mathematically. Now, to find EMF, the total EMF, which is the potential difference between the two terminals, you will find it by taking the V load, which is the external voltage, and you will add the internal voltage. So we will take V load plus V internal using this formula right here, which means that if I wanted to calculate my external voltage, I will just take the total EMF, which you can find by calculating or measuring the voltage of the battery before you connect it to a circuit, and then subtract the internal resistance, the internal voltage. Remember that we use the total current in either case. We only change the resistance. Now, let me just clean up this equation and make it more attractive. So my EMF will be given by the V load, the external voltage, which is given by current multiplied by external resistance, plus the internal voltage, which is given by total current, the same current I used here, multiplied by internal resistance. Now, if we take the current as a common factor here, that means that my EMF is given by current multiplied by external resistance plus the internal resistance. This is my favorite equation, and we will use it a lot in the problems that I'm about to do. So let's take two problems just to put this into context. Suppose that we have a circuit here with 4 external resistors. It also has an ammeter here, and an ammeter, remember that it measures current. Now, because of the position of this ammeter, you can tell that when current flows around the circuit, all of it will pass through this ammeter. Therefore, this ammeter measures the total current of the circuit. Now, inside this red dotted square, we have our battery. Now, our battery will consist of a cell and internal resistance. Now, at our cell there, that's where we will find our EMF. Now, remember that EMF is before we connect it to a circuit. Now, once we connect it to a circuit and the electrons start to move, that's when internal resistance will be induced. So now I have my internal resistance here, and I have my EMF here, and then this entire thing will give me my voltage. So this will be my external voltage, and inside I have EMF and internal resistance. Now, given the information here on the circuit, we need to find how much EMF is in this circuit. So we are calculating the EMF. Now, we are going to use one of these equations. Now, we need the total current, meaning the total current that is flowing through the entire circuit. And we said that with the position of the ammeter measures the total current. So we know that our total current is 3.5 amperes. Now, we also need the external resistance, meaning that we need the total resistance of these 4 resistors. Now, how do we calculate that? Now, I can see that resistor 1 and resistor 2 are connected in series. So I will begin with those and then add them together. My total resistance in series will be given by resistor 1 plus resistor 2. Now, that is 8.61 plus 7.82, which will give me 16.43 ohms of resistance. That is only resistor 1 and resistor 2, the ones that are in series. Now, compared to these two, the other resistors are connected parallel to those two. So resistor 1 and resistor 2 make one big resistor, and that is parallel to resistor 3 and resistor 4. And to calculate resistance in parallel, we'll take 1 over resistance in parallel. And then we add up all those resistors that are in parallel, but we take the inverses. So we'll take 1 over R series, which will be our 16.43 plus 1 over R3, which is 4.79 plus 1 over 3.33, which is resistor number 4. So these ones form one resistor since they are connected in series, and it is parallel to the other two resistors. And we add all those up to get 0.57 ohms. But this is the inverse, so we'll need to invert this to find R parallel. So R parallel will be given by 1.75 ohms, which is the inverse of this. So we just say 1 over 0.57 to get the total resistance in parallel. Now, this is the total resistance of the entire circuit. Therefore, this represents R external, excluding the internal resistance, which is equal to 0.181. Now, I have internal resistance, I have external resistance, I have the total current. All I have to do now is calculate my EMF. So it will be given by total current is equal to 3.05 multiplied by external resistance, which is 1.75, plus internal resistance, which is 0.181. And that will give me my EMF as 5.89 volts. Now, EMF is potential difference, so it is measured in volts. So now in this example, we have another circuit, and instead of resistors, we have electric bulbs. Now, every bulb has resistance of its own. And in this case, we have a bulb that has 5 ohms, another one with 3 ohms, and the last one with 6 ohms. Now, we are supposed to calculate these three: the current flowing through the battery, the voltage across the 3 ohm bulb, and the total power supplied to the battery. And I have written the formulas for power here so that we can choose which one we want to use. Now, to calculate the current flowing through the battery, we have our formula here that links the external voltage to the EMF. Now, I will just rearrange it. EMF is equal to V plus IR. Now, remember that our voltage, we can get it by using Ohm's law. So this V can be IR plus I internal resistance. Take out the current as a common factor. We have external resistance plus our internal resistance. Now, I have the EMF, which is 21. I have my EMF, which is 21. I do not have my current. That is what I'm trying to calculate. I have my external resistance. Now, my external resistance is the total resistance of all these resistors, the 3 resistors that we find inside the bulbs. Let's just calculate that quick. Now, these 2 bulbs are in parallel, so we can start by calculating the resistance in parallel. It is given by 1/3 ohm plus 1/6 ohm. Now, total resistance in parallel will be equal to 1/2. Now, when we invert this, that means that our parallel is equal to 2 ohms. Now, that's the resistance in parallel. Now, to find the total resistance, the external resistance, we need to take the resistance in parallel and add up the 5 ohm resistance. So that will be 2 plus 5 ohm, which gives us 7 ohm. So here our total external resistance will be equal to 7 plus our internal resistance, which is 0.9. Now we can calculate the current flowing through the battery, which will be equal to 21/7.9. That is 2.66 amperes. Now we have the total current flowing through the battery. It is 2.66 amperes. So let's do number 2. Number 2 says calculate the voltage across the 3 ohm bulb. Now, we know that we can calculate the total voltage using this formula. But once we find it, how can we find the resistance here? Now, how can we find the voltage at the 3 ohm resist? Now, this bulb and this bulb are in parallel. Therefore, the voltage here and the voltage here are equal. But that voltage is not equal to the voltage at 5 amperes because this collectively are in series with the 5 ohm bulb. This means that the 5 ohm bulb and these two collectively are potential dividers. So the potential difference of the 5 ohm plus the potential difference of the 3 ohm will give me the total potential difference. Remember that this will be equal to the 3 ohm. So whether I use this one or use this one, they are both equal. So what I'm going to do is that I'm going to find the voltage at 5 ohm and then subtract it from the total voltage so that it gives me the voltage left here. and we know that that voltage will be for both. They'll be equal in that way. So what is my total voltage? That will be V equal to EMF minus current internal resistance. Now my EFF is 21 minus my current, which we found that is 2.66, and my internal resistance, which is 0.9. This means that my V will be equal to 18.61 volts. And now that I have the total voltage of the circuit, I can find the voltage at 5. Now, the voltage of the 5 ohm resistor will be equal to V equal to IR. Now, the current that flows through the 5 ohm is the total current of the circuit, which is 2.66. Remember that the current is divided when the when the components are parallel. So the current will come here, and be divided here into here and into the 6 ohm and into the 3 ohm. Some will pass here, some will pass here, and then they will keep going until they meet again here. And then when they pass here, it is now again the total current. It is the total here divides here, so that it flows into different paths and then collects here, and then when it passes here, it is total. So I will use the total current, which is 2.66. Now the resistor there is 5, which means the voltage of the 5 ohm resistor is equal to 13.3 volts. Now when I subtract 13.3 volts from 18.61, that will give me 5.31 volt, and that is the volts of the parallel connection. Now I'm subtracting the total and subtracting the 5 ohm, meaning I'm left with the parallel, which means that this experiences 5.31 volts and this one experiences 5.31 volts. So that means that the voltage across the 3 ohm bulb is 5.31 volt. Now let's continue to do the last one, total power supplied to the battery. Now inside the battery, instead of using the V load, which is the voltage due to external resistance, we are going to use the EMF, because in this case they don't want total power in the circuit, they want the total power supplied to the battery. So we will use the EMF. So now when I take my equation here of power, I will take the first one, which is P equal to VI. Now instead of using the total voltage, I am instead going to use the EMF, because in this case I'm working inside the battery. So my EMF is 21 and my current is 2.66. Therefore my power in the battery will be equal to 21 multiplied by 2.66, which is 55.36. Now power is measured in watts, so you have 51.36 watts. Now even if I use the other equations of power, I would have used power is equal to EMF squared over R, and that is only because the question wants the power that is supplied to the battery. But if we're talking about a circuit or a component outside of the circuit, I would have to use the voltage.